In a serious head-on collision, the front of a modern car is designed to destroy itself as violently and completely as possible. That destruction is not a design failure. It is the single biggest reason people walk away from crashes that would have been fatal 30 years ago, and almost none of it happens by accident. A crash is really just a problem of stopping very quickly. When a car traveling at highway speed hits something solid, the vehicle itself stops in a fraction of a second. But the human body inside it, obeying basic physics, wants to keep moving at that same speed until something stops it too. The entire goal of crash safety engineering is to stretch out the time it takes to bring a person's body to a stop, because the force felt by that body is directly tied to how quickly the deceleration happens. Stop in 1/100th of a second and the forces involved can be lethal. Stop over 1/5 of a second instead, and the same crash can be survivable. Crumple zones exist purely to buy that extra fraction of a second. The front and rear sections of a modern car are deliberately engineered to be weaker than the passenger compartment, not because engineers ran out of steel, but because that structural weakness is the entire safety feature. Engineers build in what are called trigger points, specific creases, thinner sections, and pre-shaped folds in the metal that force the structure to buckle in a predictable, controlled pattern rather than crumpling randomly, or, worse, staying rigid and transferring the full force straight into the cabin. As the front of the car folds in this planned accordion pattern, bending and tearing metal absorbs a huge share of the crash energy before it ever reaches the people inside. While the front and rear of the car are built to collapse, the passenger cabin is built to do the opposite. Engineers construct it as a reinforced safety cage using some of the highest strength steel in the entire vehicle, concentrated specifically around the doors, the roof pillars, and the floor. The entire strategy only works because of this contrast. A soft, sacrificial structure out front that absorbs energy by destroying itself, attached to a rigid, unyielding shell that refuses to deform around the people inside it. Get that balance wrong in either direction, either a cabin too weak or a front end too stiff, and the safety benefit disappears. Not every piece of metal in a crumple zone is the same. Engineers select varying grades of steel throughout the structure, using softer, more ductile steel in sections meant to absorb energy by bending, and much higher strength steel in sections meant to redirect force around the cabin instead of into it. Some manufacturers also build crumple zone components from engineered plastics and composite materials, which can be tuned to absorb energy in a very specific, repeatable way while adding far less weight than an equivalent steel structure. None of this is arbitrary. Every panel thickness and material choice in that front structure is the product of computer crash simulations run thousands of times before a single physical prototype is ever built. Manufacturers cannot simply claim a car is safe. Before any new model reaches showrooms, it goes through a battery of standardized crash tests run by independent safety agencies, not just the manufacturer's own labs. These include full-width frontal impacts straight into a rigid barrier, offset frontal tests where only part of the car's front end strikes the barrier, side impact tests simulating another vehicle broadsiding the car, and rear impact tests checking whiplash protection. Each test uses instrumented crash test dummies loaded with sensors that record exactly how much force reaches the head, neck, chest, and legs. And the results are what actually earn a car its published safety rating, not the manufacturer's marketing claims. Electric vehicles have forced engineers to rethink crumple zone design from scratch. Without a large internal combustion engine block sitting up front, there is often more physical space available for a longer, more effective front crumple zone, which sounds like a straightforward win. But that same vehicle now carries a large, heavy battery pack low in the floor, and that battery has to be protected from crash intrusion just as carefully as the occupants do, because a punctured or crushed battery pack introduces its own separate hazard involving thermal runaway and fire risk, not just a structural one. As a result, many electric vehicles now include additional structural crumple zones along the sides and rear of the floor pan, specifically to shield the battery, on top of the traditional front-end structure protecting the people inside. The added weight of that battery pack also changes the physics of every crash the vehicle is ever involved in, since a heavier vehicle carries more kinetic energy into an impact, which is one reason regulators have had to revisit crash test weight assumptions that were built around a century of mostly gasoline-powered vehicles. It's tempting to assume that a larger, heavier vehicle is always safer to be inside during a crash, and in a one-on-one collision between two vehicles, mass genuinely does matter. But size and weight say nothing about whether the crumple zone itself was engineered well. A large vehicle with a poorly designed front structure can still transmit dangerous forces into the cabin, while a smaller car with a carefully engineered crumple zone and a strong passenger cage can outperform it. This is exactly why independent crash test ratings exist in the first place. Because a badge, a price tag, or the sheer size of a vehicle tells a buyer nothing reliable about how well its specific structure was designed to protect the people inside it during an actual impact. The next time you see photos of a car with its entire front end folded like paper after a crash, that is not a car that failed. That is the crumple zone doing exactly the job it was engineered to do.